Hi guys, welcome to this video on linear operators and differential operators. This isn't really going to be a video covering what they are and how to sort of work with them, but rather on proving whether one is self-adjoint on an inner product. So here we've got an inner product, and this is our linear operator. In this case it's the Hermite operator for the Hermite differential equation. And this stuff is really useful. If you're able to show self-adjoint, there's lots of methods that you can use to solve it and find nice solutions to the differential equation. Now, the reason I picked this one is because it's got two derivatives here, and we'll see why that sort of creates a problem. And one of the really smart methods we can use to solve it, and just sort of a little hint before we even go through it. The hint is going to be a similar method to solving this differential equation. So it's going to be a similar method to this. This is just a first order differential equation. We're going to somehow use one of the tricks that we used to solve this, improving that this up here is a linear operator, is a self-adjoint linear operator on this inner product. So first of all, what is a self-adjoint linear operator? Well, it means if I take this linear operator and I act it on F like this inside my inner product, then it should be exactly equal to this. So that's going to be what our definition of a self-adjoint operator is. Now, what does this look like and how do we sort of lay out these proofs? Well, we're usually going to start with one side and we're going to try to get to the other. So, in other words, our left hand side is the integral from minus infinity to infinity of e to the minus x squared. Now, doing our linear operator on f, we get f prime prime, so the second derivative of f, minus 2x f prime, like that. And then that's multiplied by g with respect to x. And now on the right side, it's going to be exactly the same, but instead of f, it's g. Like this. Okay, well this isn't really a proof though, this is just showing what we're trying to get. We're going to be starting with this side, and we're going to be trying to get to this thing. So, let's have a look. So first of all, what's the key difference between these two? Well, clearly g has not got any derivatives, and f has got derivatives. That's the key difference. So we're going to want to remove them. And the method with this is always going to be integration by parts. So integration by parts. Now, if there was only one f derivative, it's quite simple to do. You just integrate the f derivative, you differentiate the rest until you get to the right amount of power on g, and you have no derivatives on the f. So it's quite simple in that case. But when it's two, generally most people are going to split them up. So they'd work on the f prime prime one, solve that one, get that to f, and then do the same for f prime. But sometimes that can be quite long. So what we want to do is we want to first change it using a similar method here. So the method that you use for solving a first order differential equation is that you find something that when you multiply both sides by, you can change the left hand side to the product rule. So in other words, you want a function, I'm going to call it I of x, it's our integrating factor, such that when it's multiplied by y and differentiated, you get y dot plus f of x y. Kind of. You'd actually get ix, and then you get some other derivatives. But the main thing is, I want to be able to get this integrating factor like so, multiply both sides by it, do the product rule like this, and then usually we can just integrate both sides and we can find y. That's usual sort of step for this. And we know that the integrating factor is equal to e to the integral of f of x dx. And that's a little fact that's really useful. The integrating factor is this. So how do we do it in this case? Well, I want to rewrite this as f prime I of x d by dx, because then I just set that as my dv, and then by doing parts I can really simplify this quite nicely. Now remember, I of x is e to the integral of f of x, so in this case f of x is minus 2x, so we're going to get the integral of minus 2x dx, and that's going to give us e to the minus x squared, like so. So in other words, if I multiply through by e to the minus x squared, I can just do the product rule. So what I get is e to the minus x squared f prime d by dx. Now be careful, because we multiply through by e to the minus x squared, we've got to divide by it on the outside. So we'll divide by e to the minus x squared on the outside. We're still left with a g, and we've still got an e to the minus x squared that we haven't touched. And this is our integral. So we've actually changed nothing. And you can check this. You can expand this using the product rule. So we'll quickly do this. So derivative of f prime is f prime prime. Derivative of e to the minus x squared, well, that's minus 2x e to the minus x squared, and we times it by f prime. But remember, we've got the 1 over e to the minus x squared on the outside, which is going to cancel with them, and we're just left with this, which is really nice. So we can sort of check there that this does in fact work. Okay, nice. Now we can clearly see these two things are going to cancel. So what we're left with is well, u is everything that isn't part of this d by dx. So in this case, u is equal to g. So du is equal to g prime. dv, well, that's equal to this thing by dx. So e to the minus x squared f prime d by dx. So v is equal to e to the minus x squared f prime. Like so. And that's really nice. So we're going to get g e to the minus x squared f prime minus infinity minus the integral from minus infinity to infinity of g prime f prime e to the minus x squared dx. Like that. Well, putting an infinity into this gives you e to a really big negative number, which is practically 0, and you can sort of check this out with the limits. And likewise, putting minus infinity in, you're going to get 0. So this thing goes to 0. Now this thing is a lot easier now to solve. We've only got one f derivative. However, we want to get 2 g derivatives. So we set dv is equal to f prime. Let's get rid of the f prime. So that means v is f. Now u, well, that's going to be g prime e to the minus x squared. So du is equal to g prime prime e to the minus x squared minus 2x g prime e to the minus x squared. Like so. I'm going to fill in this area. So rewriting this at the top here, we're going to get minus, not forgetting this minus here, f g prime e to the minus x squared between minus infinity and infinity. Now the minus cancels because we've got this minus here. There'll also be a minus here. So that cancels. It's always really key to be careful with the minuses. And we're left with f times g prime prime e to the minus x squared minus 2x g prime e to the minus x squared dx. And well, using the same logic as before, this thing goes to 0, and we're left with the integral from minus infinity to infinity. Let's put out the e to the minus x squared. We've got f, and we've got g prime prime minus 2x g prime dx. So you can see this is actually not too bad. We're just using a fact that we learned in first order differential equations, using this little trick of finding an integrating factor. In this case, the integrating factor makes it a lot easier. You can try to do it by splitting it up, not doing this method. It's going to be a lot trickier, especially since you're going to have minus 2x g e to the minus x squared as something you're differentiating, which is a three-way product rule, which isn't the nicest thing in the world to differentiate. However, by splitting it up like this, you're not really doing any hard integration. Here, well, we're just integrating a derivative, so it gets rid of it, and here we're just differentiating one function, so it doesn't get that difficult. Here, okay, yeah, we have to do product rule and chain rule, but our integral is literally just integrating f prime, and we get a really nice solution. But yeah, these are super useful functions, super useful. They serve a lot of use in differential equations, and differential equations themselves serve a lot of use. But yeah, hope this was helpful. See you in the next video.